Yeah, so today I plan to finish the discussion of the uniqueness result of the Lawsons and to begin talking about the index computation for a particular subfamily, and both projects are joint with Nikos. So last time we reviewed Lawson's construction. Yeah, so okay, yeah, so okay, yeah, so the picture here is that we have the numbers m and k determine 2m points on C-perf and C-perf. Sorry, 2k points on C-perf, 2m on C. Okay, and we determine also these tetrahedra. So let's see, we have yeah, with spherical faces, so the faces being spheres through C and also spheres through C-perf. Okay, and so we have this tessellation, and there are we define also this this symmetry group. So we have this collection C Q is the collection of K and circles, which are in well, some of their arcs are in red here. So those are the great circles where the spheres in our collection intersected. Orthogonal to. So the great circles which pass through the marked points. Okay, and we also define this symmetry group GCQ. But I guess I was using hats for collections. I'm trying to do that. This is a subgroup or generated by all the reflections through these circles. Yeah, okay. So another way to say, I guess, describe CQ is it's all of the edges as the union of the edges. So the union of the CQ circles is the same as the union of the edges of the tetrahedra minus the edges that are on C and C-perf. So just those edges. And the idea was we solved, Lawson solved the plateau problem in one of these tetrahedra, a single one, and then applies this group. And we get our surface. Okay, but one thing which I pointed out last time I want to repeat is that this this group does not act transitively on the collection of the tetrahedra. So I call it one of these a single one in omega. So the collection. on omega hat. Okay, instead there are two orbits. Okay, so we can index these guys, and if I reflect through one of these edges, I go kind of so if I reflect through this one, I'm going to be moved this way, but also up. Yeah, so I miss when I apply this reflection group. I take I always will, if I apply one of those reflections, I will take a tetrahedron to one, never to one which is adjacent to a face, which shares a face with that one. So I get these two, which I can call big odd. Okay, and so if you depending on which tetrahedron you start with, you could generate a different surface, but they will be congruent, given that we have to do this. Okay. Okay, we established uniqueness and graphicality of the disk. So if there's a tetrahedron, we have this C and C perfect. So this is C and here's C perfect. And this all yesterday, which is the great circle through the midpoints of the edges on C and C perp. It's where two bisecting spheres intersect. And we looked at rotations, the one parameter group of rotations along L, and say this direction, well, group both directions. Okay, and we established this deepness, the D. And so we established this uniqueness result that there's only one solution to the plateau problem, but actually you don't even need to assume that it's a disk. And Q was, again, whoops, it's a different color. Okay, so Q is the quadrilateral of the edges in that line circles in CQ. We also have graphicality every orbit. Okay, this graphicality. So the graphicality will be useful when we talk about the index. It also establishes the embeddedness, although Lawson proves that in a different way. Okay, so now I want to, so I want to continue and give you a stronger uniqueness result. But first, actually, I want to talk in slightly more detail about the symmetry group of the Lawson surfaces. Okay, so we have this group of reflections through great circles. Again, another group that I want to look at is the symmetry group of the Lawson surface M. Talking about the self-congruences. So I want to say, describe that group a little bit here. Okay, and so I'm going to find another collection of great spheres now. And so last time when we were talking about the construction of the Lawson surfaces, we started with these great spheres, which give you the walls of the tessellation, end up giving you the faces of the tetrahedron. Now I want to talk about a different collection of great spheres. It's going to be, again, a collection of K of great spheres, but they're going to be the bisectors. So like the bisectors that I mentioned for this tetrahedron. No, sorry, not K. K great spheres. Spheres. Super, which are bisectors for those tetrahedra. So, or you start with the original, I think I had called it sigma hat, C or C or something like that, for the two cases, and you take the bisectors of those. Okay. Okay, now we're going to find the group G sigma hat, which is just going to be reflections through all those spheres. Okay, and because we have the uniqueness, we know that those will definitely give symmetries of the Lawson surfaces, because such reflections will preserve the quadrilateral Q. Well, not quite true that it preserves that anyone preserves a given quadrilateral, but it preserves the union of the quadrilaterals. So let me just say by the unions. Yeah. So what I should say is that if you take any of those spheres, it's going to preserve the each of the even amount tetrahedra, and will preserve the collection of the great circle CQ. Okay, so then by the uniqueness, then G sigma hat is going to be a subgroup of G, what we call M sim. Okay, and yeah, these groups depend on K and M, but I'm dropping the notation. Okay, and also the way that I did the construction, the GCQ group also is going to do that. So we'll define a group, which I'll just call G, depends on. The group generated by these two groups. So G sigma. Okay, so the reflections through the great circles of the CQ and the bisecting spheres, and that group will also be a subgroup of the symmetry group. Okay, so we know that our surfaces have all these symmetries. Okay. Order of G is going to be 8 km, right? We have this explicit description of it. You can compute the order. Okay, so we know that we have these exceptional Lawson surfaces, the great spheres, and this very special one, the Clippert torus. And those obviously are going to have those have infinite symmetries, and so this group will be a proper subgroup G in that case. Also, there are other special, not as special as those, but also special Lawsons, which are a bit different, which are the diagonal ones. Where you have the two parameters being equal, those also will have additional symmetries. Okay, which are not hard to identify, but not important for us to do. Okay, but in all other cases. Actually have equality. Okay, and you can check this using, for example, the umbilicus. So. Okay. Okay, so now that I've defined that group and said a little bit about it, I can state the uniqueness result. Yeah, let me use this animation runner. So suppose that I have some closed embedded minimal surface. With genus, the genus of a Lawson surface. There's MK, so for some K and M. And suppose further that it's invariant. Under the corresponding G for the same M and K. And the conclusion is that S is congruent to Lawson surface, so either S is equal to the Lawson surface, but well, we already know for sure that there's at least one other surface which has the same symmetry group and the same genus, which is that complementary Lawson, the one that occupies the other order of the reflection through circle group, wherever it is. Or okay, but those two are congruent because again, from the uniqueness, we know that has to be the case. So I can take yeah, so I can rotate along C by pi over n, and that will translate. So this guy is the complementary Lawson. Okay, so that's the characterization. Okay, so I'll go through the proof now, and for the first few steps, or really right up until the end, I'm just going to use the group G sigma actually. We'll use also the genus. We won't use the form. Okay, so we're very interested in whether or not you can relax the group. We don't know. Okay. Right. Okay, so we're going to look. We're going to start looking at this group. I guess it's sigma hat, and there's a tessellation that I can think about with that group, which is I just cut by all of those spheres. So we started the construction of Lawson by a tessellation by great spheres, and now I have this other collection which is the bisectors of the original ones. So I'm going to get another tessellation with a tetrahedron. Spherical tetrahedron. Which is congruent to the ones we were talking about before. Okay, if I want to talk about, I'll try not to refer to the collection very much, but if I want to talk about that new collection, I'll put an underline under it for to make me think of reflections, because they're spheres of reflection. Okay, and I'm assuming that I have some S with right satisfying these assumptions. Although, as I said, I won't be using the reflections through through the great circles until later in the proof, and I'll point it out when we do. Okay, so I'm going to look at just one of these tetrahedra now, omega bar, and I'm going to look at the intersection of S with that tetrahedron. One thing that I can say is that S has non-empty intersection with each face of omega bar. Well, just because the faces of omega bar, they lie in spheres, and S by the maximum principle, S has to intersect every sphere. You can say much more, but definitely that. So S is going to intersect every sphere in this collection, but the symmetry group, so here we use fact, which I should have written down first, is that that this group, so the GCQ group did not act transitively on the corresponding tessellation, the tetrahedra, but this symmetry group does act transitively on this guy. That acts simply transitively. Okay. Yeah, and so if I know for sure that S is going to intersect each sphere in the collection somewhere, and then I can apply the group and be sure that it intersects that particular face. Okay, and because again by the symmetries we know if this intersection consists of, it is a union of topological circles and segments. Yeah, it's orthogonal, it's transverse. So the segments there are segments, and the endpoints on the edges of the face, so in particular of omega. Okay, and again by the orthogonality, they're geodesic. So S is yeah, I have these spheres of reflection. These curves lie in, and they're going to be geodesics in S. Or on S. Okay, and Yeah, I'll call the endpoints vertices, but I don't want to confuse them with the vertices of the tetrahedron, so I'll call them polygon vertices. Okay. Okay. And we know, so we know that if we have a vertex at all, angle theta t. Yeah, so if I have a vertex, that means right, I'm looking at where S crosses my the face of the tetrahedron. The vertex is going to be where it hits an edge, and the angle there is going to have to be the dihedral angle. And this is just because the intersection is orthogonal. Okay, and I should also have said that you cannot have the polygon vertices. A polygon vertex cannot be at a vertex of the tetrahedron. Yeah, so S has to miss the vertices of the tetrahedron because of the orthogonality. The normal has to be point along the edge. Okay, another important, but also all really basic observations. The intersection of S with omega, so not just the base, is itself connected. Why? Because S is connected. Yeah, and again, we have this transit action. So yeah, I mean, it's more than that. It's because specifically I have the reflections. So I have this tessellation by tetrahedra, and I know that any 2 points in this intersection are definitely connected by a curve on S. So if the curve that I pick happens to leave the tetrahedron, I can just reflect it back in to the basis. So we get the connectedness. Okay. Okay, so I have these nice intersections of S with the faces of omega, and yeah, I know that it's a connected surface inside, so I can apply now Gauss-Bonnet. So yesterday when I talked about the construction of the Lawsons, we looked at computing the genus using Gauss-Bonnet locally and globally, right, on a patch and globally. We can do the same thing here to get some information. Okay. So what do we get? Object what we get. Okay, well, yeah, so I have the right down across the I have the total curvature term. The boundary curvature, right? The edges are geodesics. It's a piecewise geodesic, and so I only get contributions at the vertices if there are any, and that's where the surface meets the edges of omega. Okay, and I know also that these angles are the diagonal angles, so that would be helpful. Okay. Okay, but we know we can apply Gauss-Bonnet globally also. We have the symmetries, so we can compute this. We have the genus. Okay. Okay, so doing we get an expression which of course is going to involve K and M, and yeah, I didn't say that G and B are the genus and the number of boundary components at this intersection. So, okay, and so refer to this equation a few times, so left-hand side and right-hand side. Okay, and so now the idea is just to exploit this as much as possible, and so maybe I'll go through a few points and skip a bit. Let's see. Okay, so first of all, okay, first I can conclude that the intersection actually is a disk. So I mean, G is 0, and B is 1. Okay, if not, then I know that this quantity 2G plus B is going to be at least 2. Okay. Okay, so the right-hand side will be strictly less than pi. And you guys should also say that we're assuming that A is at least 2, and M is at least 3. right? If I have k equal to 1, that gives me the great spheres. I don't need to worry about those. We have much stronger uniqueness. And the Clipper torus is k equals 2 and n is equal to 2. So we won't worry about this. Okay. Okay, but on the left-hand side, again, we know that the only angles which can show up are the dihedral angles, which we know. And so the only possible dihedral angles are pi over j, and pi over 2. And I know I'm making these assumptions about k. So on the other hand, I have the left-hand side has to be at least pi, so we can't be in this case. Okay, so in particular, I'm not going to have any topological circles. I'm just going to have segments. I'll start calling them sides. So I know that this intersection is the boundary is a geodesic polygon, and I know that I can have at most 5 sides. Again, I just use this fact. So. No, I know that the right-hand side has to be less. I know now that the right-hand side has to be strictly less than 3 pi. But I know the dihedral angles that can show up, and I have these inequalities, and so. Okay, so we have fewer than 6 vertices. Okay, we also know that we have at least 4 sides because we've already noted that each face must intersect. Yeah, so I'm using the word side for a side of the polygon, what I was calling segment earlier, and edge toward the edge of the tetrahedron. So tetrahedral edge. Okay, so yeah, we know that no edge can contain more than 2 vertices. Polygon vertices. Yeah, otherwise I would have to have, well, I have 2 adjacent faces, and both of them would have to have at least 2 sides. If the other faces have at least 1 side, then probably the max number of sides is 5. Okay, and you can also note that if I do have an edge which has two vertices, then I must be in the case where I have five sides because yeah, because I have just one boundary component, at least one of the adjacent faces will have two sides. Okay, so I have either a quadrilateral or a pentagon. Yeah, and actually, I mean, I'm giving you the argument that we wrote in the paper. Not really sure. So eventually, we rule out the pentagon pretty soon by using the bigger symmetry group. I'm not really sure that's necessary. I think maybe you can rule out the pentagon, but that's not what we did. So so we'll pursue that. So let's look at what we can say a little bit more in the two cases. So the quadrilateral case. Okay. And so just that in this case we can't have two vertices on a single edge. The missed edges, so I just mean the ones that don't have, the ones that are missed by S, so they don't have vertices. So opposite on the tetrahedron. By opposite, I just mean that they don't share. A base. Okay, so there's a if I have an edge of the tetrahedron, I can see one that doesn't share a face with it. Okay. And yeah, why is that? Right, okay, if not. Yeah, so if that doesn't happen, then I would have to have a face, actually more than one face, but at least one face with exactly three vertices. Okay, but I have only one side of that face. Okay, and then finally, okay, so C and C perp are an example of a pair of opposite edges, and I can say for sure that S has to hit both of them, and for that we again use this equality. So because yeah, otherwise by the previous fact, so if I miss one, then I would have to miss both. Okay, but that means I don't have the pi over k or the pi over n dihedral angles. So I know that, yeah, sorry, that left-hand side is going to have to be 2 pi, I have only the pi over 2 angles. Okay. Let's see. I think now I can fix this. Okay, in the quadrilateral case, definitely happens. That's one that happens for the Lawson. As I said, I'm not sure. Maybe it's easy actually to rule out the pentagon case, but let me just include what we can say, which is going to be enough to rule it out when we impose the additional symmetries. Try to draw a generic tetrahedron to describe it. Let's see. Okay, so one observation is there's a face with 2 edges. Sorry, two sides rather. Yeah, we have five sides, right? Every face has at least one side, or one of them will have to have 2. So let's say that's the first face. The front face here. Sides. Okay, so there are 2 sides on this 2 segments. You have 2 sides of this face, and so I'm going to have 4 vertices. So at least one of those edges then is going to have 2 vertices. We've ruled out that we can't have more than that in the previous step. And so one edge. And so there are two more vertices, but I haven't determined yet where they are. Yeah, so I have 2 more vertices. Sides and 4 vertices. Okay, so there's one more vertex with this pentagon, and what can we say about where it is? Well, yeah. So the remaining vertex. Yeah, so one edge has these 4 vertices. Let me just call it E1, and the remaining vertex must lie on the edge on the opposite edge of the plane. So you can prime. Okay, and the reason for that is if not, yeah. Right. Yeah, it cannot lie on F0. Yeah, it can't be on an edge on this face. We already have 4 vertices. We can have 5 here. And we can't, that's not compatible with the, yeah, we can't have an odd number of vertices. With the two sides. Okay. And it also cannot lie on F1. So F1 would be this face here. Since I have these two guys here, then I would have a face with 3. And I also cannot do that because I know I'm just going to have one. Going to have exactly one side of that face. Okay. So this has to be a picture. I have to have one here. And then, okay, then each edge of each remaining edge. So if I had say 2, then I would end up with a face that just can't have an edge on it. So okay, so that has to be the picture in the pentagon case. Okay. Yeah, so that's why we've just been using the reflections from the big spheres. Now we'll use the reflections from the big circles. Okay, so now I can say that in either of the 2 cases, it's definitely true that if I look at the 2 opposite edges on the CNC verb, at least one of those is going to have exactly one vertex. Yeah, so in the quadrilateral case, actually, I know that S means both C and C verb. And in the case of the pentagon, yeah. So the only, yeah, there's an edge which does not have a vertex, and there's an edge which has 2. But C and C perp are opposite one another, and so that's not compatible with that picture. Right. Okay. And so, yeah, I was talking about the axis of the tetrahedron earlier in the uniqueness proof, the uniqueness of the disk. So that was the tetrahedron in which we solved the plateau problem. And now we're looking at like this kind of these dual tetrahedra where the faces are spheres of symmetry instead. Okay, and so there's these are shifted relative to one another in such a way that the axis of this omega, so what I mean is intersection of the bisectors of this guy. So the bisecting spheres those bisecting spheres are the spheres in the original collection from the construction earlier. And so their intersection is going to be a great circle in CQ. The axis here is going to be one of the circles which can be used for plateau data in the construction. Okay. Yeah, it follows that, so this vertex, so we have at least one of the edges of CC perp has exactly one polygon vertex, which I call V. So since I have these symmetries and I have exactly one vertex, it has to be on L. So we must lie on L. Yeah, okay. Okay, but yeah, L is a circle of symmetry for S, and I'm going to have, and S is not a Greek sphere, so I'm going to have orthogonality. Okay, so we can conclude that L is contained in S because we've just determined that the intersection of L and S is tangential at this vertex. Okay, but this is a great circle of symmetry. Okay, so now we know that this great circle actually lies on the surface. Mm-hmm. Mm-hmm. Okay, so we now know that so we got here from the observation that at least one of these edges would have exactly one vertex, and then we determined that the vertex is going to be where L intersects, and then L is on there, but L is on there, so the N is a symmetry, and so the other edge is going to have an odd number of vertices. So both of them will have an odd number of vertices because of the other symmetries. Sorry, yeah, the number of vertices. Okay, but they're C and C perp are opposite, and that's one way you can rule out the depending on case. Yeah, and I wouldn't be surprised if you can rule that out without this argument. But okay. So we know we're in the rectangle case, and we know that we contain the quadrilateral case, and we know that we contain L. Okay, so I have this quadrilateral. I'm going to cut out L, and then I cut, yeah, from this information, I know that I cut into two triangles. Okay, and I'm going to focus on one. Okay, so I have this triangle, and now I want to get to a situation where I can use the uniqueness of the Lawson disk. But I don't have that, right? I have one side, which will be one side of Q, which should be, right, one of the Q's, which is the Wiygul data. So I cut, and now I know that the other two sides, they're geodesics that lie in spheres of symmetry. So these are sim. Yeah, because these are on the faces of the omega bar. And so I can reflect through them, sorry, reflect in S3 through those faces. So extend. Through the spheres. Containing the other two sides. Okay, so we do this one reflection and the other reflection, and in that way you get we get a quadrilateral. Yeah, and its boundary is going to be given by L and its reflections, and so that will be yeah. So L lies on one of the grid circles in CQ, and the other edges two, and in fact these will be the edges of some tetrahedron in the original. Yeah, the edges off of CNC perp of some tetrahedron in the original tessellation. Boundary. Yeah, Q for some tetrahedron. Okay. Okay. And now we can almost just apply the uniqueness result, except we're not guaranteed that D prime lies in omega ij. That's one valid objection. Okay, but right, we got this by taking something which was a piece of the intersection with omega bar, and then we did the extension. So we're guaranteed at least it's contained in extension of that omega bar by those reflections. reflections that we use to extend T prime. And that's enough then to use the maximum principle. Yeah, so I know that this disk lies, yeah, I know that it has boundary some Q, and I also know that it's going to intersect some omega ij, right? So I take that omega ij, a priori, we don't know that it doesn't spill out, but we know it can't go too far, so we can use the maximum principle. It doesn't actually go out. And then, of Lawson disk. So that's the proof of the uniqueness of the disk. Sorry, of the surface, the characterization of the surfaces. Okay, yeah. So I would be interested to know if you can go, how much farther you can go just using, say, the reflection through spheres or some Wiygul group. But I don't know. But I'd be very interested in that. Okay, so then the next thing I want to talk about, of course, is the index, and I can at least start a little bit. So index. Okay, so that previous result applied to all of Lawson's embedded surfaces. The Morse index computation we can only do for this subfamily. So in Lawson's notation, we have CG1. So this is a subfamily which does realize every possible genus. But annoyingly, we use this different notation, which is convenient. You'll have m showing up a lot rather than G+1, but okay. And so in the notation that I'm going to use, this is NM2, so K is equal to 2. Okay. So quickly the definitions. So if I have some closed embedded minimal surface, I don't really need the embeddedness, but we will yeah. Well, if I have a normal new. And I want to consider normal variations of the surface, right? So these are minimal surfaces, and they're critical points for the area functional. We can look at the second variation of the area, study the stability and the Morse index. So we take some function. I'm going to use that to specify a normal deformation of the surface. So I have, yeah, so if I'm supposing I'm embedded. So I have the inclusion of S and S3, and I'm going to deform it by U in the normal direction. So this will take me from S into S3 again. I'll just use yeah, any normal variations. Okay, with velocity B. Okay, and then we have the second variation, and secondary area. So this is given by by the Jacobi form, the Jacobi operator. So generally there's a Ricci term, so we're in S3, so that term is going to be 2. Okay, so yeah, so the second order operator showing up, so this is the Laplacian, the second, the norm square norm of the second fundamental form. This is the Jacobi operator of S. Okay, so this is symmetric elliptic operator on a compact surface is going to have a discrete spectrum, and the Morse index S is the number of strictly negative eigenvalues minus L. Well, depending on your sign convention, but I'm looking at the directions which will make the area go down. And I'm counting with multiplicity. Yeah, so this is a measure of the instability of the surface. And the nullity is the multiplicity of the zero eigenvalue. If it's an eigenvalue, so I guess it's the measure. Okay, so the nullity of L. So for the simplest examples, you can write down the Jacobi operator explicitly and analyze the index of the nullity. So we have for a great sphere sigma, we have Laplacian plus 2, yeah, on the sphere, and so you can just compute that. We'll get index and nullity 3. Yeah, so you can do it just analytically. You can also do it more geometrically, but it's simple. For a Clifford torus, we have instead Laplacian plus 4. Now we're on a flat torus though, so again, you can just do the computation. And then I'll need 4. And the famous theorem of Wiygul. So every other closed normal surface, so if you're not a sphere or a Clifford torus, yeah, so there's we have index these 6 for short.
So, can you describe theoretically the nullity of the pivot right?
Yeah,
see the notation,
sure.
right?
So yeah, I mean, a quick way to check this is that it's at least 4 is that you have the ambient Killing field, you have a 6-dimensional space, and this has what the symmetry group, right? Is you have 2 of those dimensions reserved the torus. So that's 4 is left, and those give you for sure nullity, and nothing else gives you nullity too. I guess that has been checked. Okay. Yeah, and similarly for this.
Yeah.
Okay. Yep. Okay. Yep. Oh, all right. So we have this very important motivating result. Yes, it would be nice to be able to say more about higher genus case. Even more. And let's see. Okay, so there are some very interesting general bounds also, which I should mention. Lower bounds. And others that I mentioned. Some which are sort of closest to what we look at. So there's the lower bounds of Savo. Okay, so Savo also has results in higher dimensional spheres, but this is what it says in the 3-sphere. So okay, so in particular, we can apply this to the Lawson family. So let's see G1 is at least G4 this. And another result, which is more, yeah. So this is a result of J1 from also from around 90, I think. Okay, yeah, so in this paper, he proves a number of lower bounds for a variety of surfaces, but in particular for the Lawson surfaces. For all of the Lawson surfaces, not just this subfamily. Okay. So in particular, for the index of and we're looking at of 2G plus 1 in the cases that we care about. Okay.
So maybe it's,
yeah.
When you feeling that you want to stop it.
Okay. 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 Good. Yeah. I'll state the theorem and then we'll prove it next time. Okay, so again, let's exclude the Clifford torus and the sphere. Sorry, let me state it in yeah, I'll state it in CD1, yeah. So I'll use the Lawson notation. Six, okay, and so we have a computation, and that's what I'll talk about in the final lecture. All right, thanks.
All right, thank you very much. Is there any question for me?
No? Okay, thank you. Thank you very much.